My name is Andrei Kulikov, and I'm joined today by another Andrei, Andrei Shikov, and we both software engineers at Google working on Jetpack Compose. From you today, we expect that you have at least some experience with Compose, and probably you know how to use common layouts like box, row, and column. But in fact, today we will go custom, and we will try to implement some custom layouts, and we'll understand layout system with that. So what you can expect from us to cover? We will start with writing simple and not so simple custom layouts that will help you understand how it works. Then we will figure out what is magical about subcompose layout, how it helps you to solve some of the use cases, and when you probably don't really want to use them because their superpower is making your application a bit slower than you need. And the next one, we will lazily switch to the next topic, which is lazy layout. That will help us to implement some custom scrolling lists, and with that you probably need lazy layout APIs. So assume that your designer asks you to implement such screen. In fact, you maybe already saw the screen. That's our new sample app called JetLacked. We just released it at Android Developer Summit this week. But we actually changed some layouts in there, and we will not go into any graphics or animations. Instead, we will try to implement this graph. And basically, probably your main question is, why can't we just use columns and rows here? Why do we need to implement any custom layouts? Well, yeah, why it can be just a column with multiple rows? In fact, it can work in some cases, but maybe we have more requirements. And let's try to understand what are them. So we want to position this component we call bar. And we can see that its position probably somehow configured by the header, because for this item, this bar is representing a sleep we had, which started around 8 p.m. and ended at around 8 a.m. It is definitely more than I had of today. But actually, it is configured by header, and header will be providing some lines for you. And actually, Compose helps you to do that. We have a feature called alignment lines. And in order to use that, you will need custom layouts. In fact, we even need two custom layouts. The first one for the header, where we will be providing such alignment lines. And the second one for the whole graph. Here we'll be reading these alignment lines and apply them for the bars and position and provide the size for all the elements here.
So let's go into custom layouts. First, a bit of theory. What do we need to know about layouts? Well, you're probably aware of this scheme. It's kind of what we always talk about. When we talk about Compose, we talk on three phases. First is a composition, then there's layout, and then there is draw phase, where you draw things on canvas. Today we're focusing on a layout, obviously. And it is separated into measure, where we figure out what the size of elements are, and placement, what the position element is. And we'll do in a little bit composition, just because it's before that, and you cannot do layout without doing composition. The entry point to all the custom layouts is the layout composable. In fact, like most of the things that you use in Compose, in the standard UI library, is implemented with this layout. So here we have a few things to consider. First is the content. It's the children of this layout that will be composed into it. Second one is the modifier. All the things that use modifier for will be applied here. Maybe interaction, maybe like some padding, or like drawing in background. And the last thing is a measure policy. And this is the logic of a layout, the meat of it. We get measurables. This is the children that we compose from the content. We get the constraints. This is the size that parent expects from us. And we can just figure out the size of the measurables in the measure, and then position it in a placement. So as you may see, the placement is actually happening in a layout block, which is like a DSL that the Compose uses to ensure that you cannot place items before it goes into placement, into second phase. And it's really useful. We'll be using this layout a lot, so take a good look at it. Let's start with the header. So it is like pretty straightforward layout with just a few horizontal items positioned one by one. We start with the composition, just trying to figure out what children this layout has. And this is the API we decided for the whole layout. So the first thing to notice here, we represented the time range with the local times. And then there is an hour step in between those, so kind of showing like how many hours will be spent in between each of the labels. And the other thing is the content for each of the labels. We want it to be customizable, so we decided to do kind of slot-based API based on the local time for each of the labels to have. The first thing we do inside this row is to figure out which labels, which local times correspond to the labels that we want to have, and then which composables will show these labels on screen. And with that, we are ready to go to measure. We know which children of our layout are. We just need to measure them. So measurement here is pretty straightforward. We have the layout width. We take the maximum what our parent allows us to have. And then we just separated the equal chunks of equal width. That's what we do here. We have the number of our measurables, the number of our children. We have the maximum width of the layout. We divide it, get the width, and then force the constraints to be exact size that we want. In that exact size, we measure the children and get the placeables out of it. And they will be each of them will be equal size. With that, we're almost ready to go to the placement and position layout because we already know the children size, but we still need to report the layout size of the header itself. And for that, we can just calculate it during this loop where we measured the children before. We just accumulate the width and take the maximum of the heights of the placeables. And with that, we are ready to position the children. But for that, we just go over all the placeables and just put them one by one horizontally, accumulating width. So each of the children will be placed where the previous ends. And that's it. We have the header. But wait, there is more. So Andrei already told us about alignment lines. So let's try to implement it while we are doing something about header. The alignment lines is pretty interesting in Compose because they allow us to report certain offsets. And then these offsets will be also available on each layout that wraps this current composable. For this layout, we don't need offsets for all labels because these labels, all of the labels are equal size. So we just take the first one, we take the last one, and then infer all of the rest of them based on those two. For the alignment lines, the API is called exactly like that, vertical alignment line. There is also a horizontal one if you want to go the other way. And what we do here is define both of those lines on the top level and then use them as the keys in a map. The value of this in this map would be the offset that this value represents. And this value will be automatically offset whenever we wrap layouts. For example, when we wrap this layout with row later, you will see that the offset that it represents will kind of switch around for the parent layout. And these alignment lines will be just reported to a layout block where reported layout size of width and will be available through the placeables or measurables later. And with that, we are ready to go to do the rest of the all.
Yeah, so how we mentioned already, it will be just another custom layout, the graph itself. Let's start doing that. That's a new layout, but we have to implement all the same phases. So we start with composition. For that, we introduce a new composable function called time graph. Here, we will actually accept a lot of slots for each part of the screen or part of the component. We will start with a header. There we put a hours row we just implemented, but we will actually wrap it into one more row and not add extra text to the left. Then we have to define the amount of lines. The lines will be represented with an object which contains start and end offsets. They are represented as a fraction, basically value from 0 to 1, and that's a fraction within the distance from the start alignment line and the end. So for example, for this bar, you can see probably it starts somewhere near 0.2 and ends near 0.9. With that, we continue to our API, and we have a slot for bars. Here we have a slot which accepts an index. So inside you have to put a content for only one bar. And same goes for labels. Then we have a modifiers, because every custom layout needs to accept this parameter. Inside the implementation, we will prepare the content lambdas. And for labels and bars, they will combine all of the labels for each line. And then we will pass it into layout composable. But note that we are using another overload here. That's overload, it accepts a list of content lambdas instead of just one. And it also gives you a list of measurables. Here we have separate measurables for each slot. This basically allows us to have a clear mapping between the slot and measurables the slot provides to you. Important to note that this layout overload is experimental for 1.3 and is on a plan to be stable for 1.4. So with that, we are ready to start measuring our children. First, we start with a header. And header, we have to measure it with constraints, but basically it's parent constraints where we removed the minimum limitations. Why so? Because the child can have smaller size than the parent itself. Because if we will not do that and someone apply, for example, fill max height on a graph, this will mean that the header will also fill the whole height. We don't want that. Then we measure our header. Not that we assume that there will be always only one child inside this header slot. That's why we call single on a list. In reality, you probably want to have some reasonable layout strategy how to handle the cases where someone put multiple layouts in your slot. Maybe it can be stacked as a box. For simplicity here, we assume that will be always one, but we want to have at least cleaner error messages so users are not surprised when they do something you didn't expect. Then we can read the alignment lines. How we do that is we pass objects for alignment lines we defined previously to the getter on the placeable. This returns you alignment line in offset in pixels. Nice thing about alignment lines is that when we were defining them in our throw, we were defining them in local coordinates. But in fact, you notice that we added extra text in a header, which means that header row is moved a bit. So now we will have the new value for alignment lines. The proper offset will be automatically calculated by the system. Then we want to measure the bars. We know that the size of the bar is defined by two fractions. First, we calculate what is the maximum available width for the bars. That's basically distance between two alignment lines. Then we calculate start and end, applying this fraction. And the distance between these two offsets is basically the size, the desired size for the bar. In order to enforce that, we will create constraints with a fixed width, and we measure with them. This returns as placeable we need. Then we can proceed for labels. For our design, we want our label's height to never be larger than the bar height. We can easily ask that with providing the constraints where we only override max height. And we measure with them. With that, we measured everything, and now we need to define the size for the graph itself. For the width, we will use the header width, but for the height, we will use the sum of all the sizes for all the lines and for the header itself. Now we can proceed to placement. Here we will place our placeables. First, header is always in the top left corner. Basically, it's 0 and 0. Then for the bar, here we again will use our fractions. Start fraction is where we need to position that. That's what we do here, and we add start line, and basically we call place on a placeable. Not that we do it in a loop, that's why we also adjust current y, so the next line is positioned below the current one. And here for placement for the label, actually the labels are expected to be smaller than the bar itself, and we decided that it would be nice that we will center them vertically within the, basically aligned to the center of the bar. That's simply to calculate when we have the heights for both of the placeables. And now we finished with the graph. The layout is ready.
All right. So we kind of finished with the custom implementation, and I hope you were able to follow the slides. Because now we switch into the different kind of layout. So we're talking about like how measure and layout works in a regular layout composable. But there is one thing that doesn't quite follow these rules. Let's talk subcomposed layout. So we already discussed some of these things, like how composition goes into measurables, which you can measure, and then later placement or layout phase. But subcomposed layout doesn't do that. It doesn't give you a place where you define the content for it. It just doesn't have measurables in it. It only provides you constraints, and then you need to figure out what the content is during measure. So to compare, there is the scheme for the layout, and here is the subcomposed layout, where inside the measure we actually create the children on the fly and create measurables out of it. The subcomposed method that provides you those measurables for the children and does all the magic requires you to provide the slot ID. Slot ID is a unique identifier of some place on the screen, some unique identifier for the child. And usually, if you put something in the same place, you want to provide the same slot ID. Then you provide the content, the actual composable thing that will be composed into that slot, and it will return you a list of measurables. And with that, you can do all the rest of the logic that we already did with the custom layout. Before we go into some examples of where subcomposed layout is used, I just want to mention that subcomposition is kind of subverts expectation of the usual layout system. With that, it incurs certain performance costs. It is very important to consider if you can implement your layout without subcomposition first, and use subcomposed layout only if you cannot. For example, one of those things that we noticed people use subcomposed layout for is when just separation of the slots. So you can see we have like 2 slot composables, and we just use these IDs because subcomposed API is kind of similar to what you want to achieve here. But again, for performance reasons, it's not really as good, especially if you try to reuse it in a lazy layout right now. What we can do instead is to use this API that we provided, we already used before, which separates the slots and allows you to destructure measurables into neat kind of separation. Or before 1.3, if you're an older version, you can use layout ID modifier, which is kind of does the same thing. But subcomposed layout was still created for a reason. So let's kind of go through the reasons why we need subcomposition. And one of those things is dynamic content that depends on the parent size or the constraints that parent requests from us. For example, here we only want to show the gray box only if it fits on screen. If it doesn't, we just hide it. And we can achieve that with box with constraints. Maybe you already use this layout. It's kind of one of the most used, I think, in Compose. One of the used subcomposed layout in Compose. So it provides us the constraints, max, min, width, height, and also all the things that box provides to us. And here we just use this max height to figure out if you want to put rectangle on screen or not. Inside of it, you will see that it's, if you just command click through, you will see it has like this constraint scope, which is propagates the constraints for us. And this is, you can just command click in a bit level further, we'll find where it's defined. Here we use the subcomposition with the key unit, so it's always the same place. And this subcomposition will create a map of measurables, and we can use these measurables to later continue layout logic as we usually do with the box. So that's kind of box with constraints, a kind of simplest example of the subcomposed layout there exists. The other thing subcomposition is really useful for is lazy. So we have a lazy column, rows, grids, and what's not. And all of those things obviously use subcomposition for a bit different reasons. So here we try to figure out what items are actually visible on screen. And if you have like 1,000 items to compose, we don't want to compose all of them. We want to only prepare what is visible right now and then do the rest on the fly. And this is exactly the definition of the subcomposition, and that's where it is. And in fact, lazy layouts have like a lot more common complexity in it. And this is what we abstracted into different type of API, and it's called lazy layout.
So yeah, the lazy layout is the API Compose provides for you in order to implement your own custom lazy lists or just lazy layouts. We already implemented the graph, but in fact it only works nicely if you have not that many of the items. Basically all of them should fit on the screen. If we have more, we want to make them scrollable. So, and in order to have a performance scrollable component in Compose, you only need to compose items which are really visible. Otherwise, if you have like hundreds of them, we will compose all of them, which is not performant at all. So let's start with exploring what is the API for lazy layout. First important bit here is that it is experimental, which means the API can change, for example, based on your feedback. The first parameter is item provider. Here you provide information about the items you have. We will discuss it a bit later. The last one is a measure policy. That's similar to how it works in subcomposed layout. Note that we do not have measurables. Why? Because we have a custom scope to measure them, to compose and measure them. Getting back to item provider, here we have to provide the amount of items we have and the composable content for all of them based on the index. But wait, how can we how can we even understand how to put something from this complex graph into the system of global indexes? Okay, let's start with just assigning, for example, index 0 to header. It will always be on the top. Then we have multiple lines, and we have 2 slots to put in there. So the first index will be for the label, and the second one for the bar. And then basically for each line we have a formula. Label index will be 2 multiplied by line plus 1, and bar index is label index plus 1. A bit complex, but still works. So here, the total items count then is lines count multiplied by 2 and plus 1 for the header. Okay, for the content, we will always emit the header when index is 0, as we agreed. For the rest of the items, we calculate the line index, and based on if index is odd or even, we will put or label or bar. Okay, that works. Then the next complexity we will have is how to make it scrollable. By scrolling, we basically offsetting the children. And when we scroll enough, some items will be not in the viewport anymore. So for example, this faded out item is not visible anymore. Basically, when we scroll down, we accumulate some scroll offset. We can agree that when we scroll down, that's a positive number, which means that scroll offset is never negative. We can't go to the top from the initial position. And with that, we need to create some state. We usually call such components as component name plus state. So it's lazy grid state. Here it will be lazy time graph state. Inside we have a property called scroll offset. We make setter private, so we control how it is updated. An important bit here is that it is also baked by mutable state, which makes it observable. All the readers will be notified when the scroll state is changed. Then we have internal property called scrollable state. Scrollable state is the object we will later provide into scrollable modifier. The constructor accepts lambda, where we are consuming the scroll events we get from the system. Here, important thing to notice is that we get deltas in float, but in fact we lay out in ints. So what we will do here is that we will make sure to only consume the int part of the float and report the part only the scroll delta we really consumed without the fractional part. Okay, so basically how it scrolls. We have some items which are visible in viewport and some items which are not yet. And we can quickly realize that we can't scroll infinitely. There is some end state where we can't scroll anymore. We can define it as when the last item is in the end of a viewport, and we can call such offset as we can call it max scroll offset. After that, we should not accumulate scroll offset anymore. So let's provide a setter for this in our state. It will be internal because we want to make sure that only we update it from our measure logic. Basically, when we have this scroll offset, we will provide that. And when we have some new value, we need to make sure that the current scroll offset is within the new required maximum. Basically, we just make sure it is never larger. But one more thing is that we need to make sure that when we consume scroll events, we are always within the bounds. That's what we do here. Okay, so our component is now ready to be scrolling. But wait, we still don't have a component at all, only state for it. So for that, we will we'll write a new composable function called lazy time graph. And in fact, it has pretty much the same API as the previous implementation. What is different here is that we have a state parameter, basically the one where we put the scroll offset. And another one is line height. What we are doing here is that we are, for the simplicity of this example, we are making sure that all the items have the same fixed size for the line. And why it helps us? Because it helps us to treat the scroll offset as absolute offset in pixels, not how it works in lazy column, for example, where we have first visible item and relative offset. And why it helps us here? Because when we know the size of the line in advance, we can always calculate the first visible index based on the scroll offset. So for example, when we have 200, the first visible index is 4. which helps us to not compose items before the fourth when we have such scroll offset. OK, now we will start using it. Basically, we call lazy layout. We provide item provider here, but we need to apply a few modifiers here. The first one is called clip scrollable container. As you probably know, layouts in Compose do not clip by default, but here we want to never display anything outside the bounds. If we will not apply that modifier, we will have items overlapping the siblings, and they will be abruptly disappearing once we figure out that this item is not visible anymore. That's not what we want, so we apply this modifier. And the next one is scrollable. That basically does all the magic for the scrolling when we pass there the scrollable state. With that, we are ready to start measuring.
Right. So measuring a lazy layout is also a bit specific. So it has the special scope, similar how Subcompose has it, and it's based on indices. We already had defined indices for the item provider, so we'll use the same scheme here. And based on these indices, we'll receive the list of placeables, we can later position. So yeah, this is the scheme that we defined for the item provider. We'll be using later for measuring the layout as well. And we start with the header, the same as before. But instead of measuring the measurable for the header, we measure index 0, which always corresponds to the header. And when it's measured, we can just define and start the alignment lines as we did in the previous implementation. And then it's the meat of the lazy layout. We actually try to figure out which items are on screen based on the scroll offset. So what we do here is first divide the scroll offset by the line height to figure out the line number, and then figure out the offset by taking the remainder of that division. And as you may notice, the offset is negative, and this is pretty confusing, especially like if you're working out which way offset goes. It's kind of weird because like scroll offset also increases, but the offset of the item will decrease when you scroll up. But if we consider where items go when we scroll down, they actually go up. That means we kind of apply a negative margin to an item, and negative offset kind of makes sense now. When we scroll a bit further, we'll reach the new line, and the offset will be reset, so it will never be more than negative line height for us. With the first line known, we can start measuring items. And what we do here, we just go over all the lines that fit the screen. So we go until we reach the final line, or until we increase the offset to the size that like larger than the parent size. Meaning like the next item will be out of the viewport. We don't need compose or measure it. We just continue, and then we measure all the items, and we stop. So that's what we do in this loop. We have the current play index. We set it up with the first line offset. We go until we reach the end, either viewport or the end of all of the lines, and increment it after we measure everything. Inside the measure, again, just a reminder, this is the scheme that we use for indices, and this is how it's implemented. So we just take the index line, multiply it by 2 and add 1 to get the label, and then we measure this label to get the placeable. It's the same for bars, but we also have this fraction logic that we had previously for the previous layout. So here we do the same, and then measure it with the constraints based on this bar logic in the index. With that, we measure the labels and bars that are currently on screen based on the offset. And the last thing that's left is to connect the state and the measure cycle. So here we already know what number of lines we have. We know what's the size of each line is. So what we need to do is to figure out this exact viewport height and figure out how far we can scroll in this layout. That's what we do here. We just subtract the total height of all lines that can be potentially measured in this layout with the current size of the parent. Before we go to the placement, we measure layout, and it's just take the maximum size of the parent here, because we just almost always have more children that the layout can definitely fit. And the placement is kind of similar to what we already saw. We just go over each element, and increase the offset in the line. I won't go much into logic there because it's basically the same as we saw before. But the interesting place is the header, because before, in the previous layout, like the regular custom layout, we were placing it first. But now if we place it first, it will be overlapping with children all the time. Like children will be scrolling on top of layout. We don't want that. What we want is to place it last, and as placement order affects the order of the drawing on the items, First, we will always draw labels and bars, and then we'll log header, which is exactly what we need. And here is the final layout with all of these things where we figure out which items on the screen, and it's labels that are scrolled up, they kind of disappear and reused later at the bottom. As you may notice, lazy layouts are a bit more complex than the custom ones. We cannot just go from the top and figure out like which items are. We need to kind of maintain the scroll offset, which items are visible, which are not. And this can be pretty confusing. This is the API, as Andrei already mentioned, is experimental. We're constantly improving it. And even if you try to implement your lazy layout, or even if you didn't try it, see something can be improved there, we really value feedback. We'll be here for the conference, or you can just submit it later through any channels. And with that, we're approaching the end of the talk. I hope you were able to follow again, and this is the things that we learned today. So the first is the custom layout implementation. We went through the custom compose phases, the layout phases as well. There's measurement and placement, and learned to use the layout primitive, measurables and placeables in the corresponding places. We also dipped a bit advanced territory and used the alignment lines to kind of communicate between layouts, which their position where the offset inside of them are. Then we went through subcompose layout, briefly just went what dynamic composition is and why it's important for the layout system in Compose, and also went through the use cases when we shouldn't use it, and then through use case when it is useful. And the last thing, we built our own lazy layout, which is kind of commendable on its own. And with that, that's it from us. There are two links on the slide. First is the sample that we use here to just give you the context, and maybe code will be easier to understand than the snippets we had in the slides. And the second thing is documentation and the custom layouts, which kind of repeats some of the parts that we already showcased today and has even more things in there.